It is a winter morning in Paris, 1902. In a modest laboratory at the Muséum National de Histoire Naturelle, a chemist named Auguste Verneuil watches a tiny bead of molten alumina glow white-hot beneath a jet of flame. Around it, crystal is forming, atom by atom, at the astonishing rate of a centimetre an hour. For the first time in human history, a ruby is being born outside the Earth. For millennia, rubies had been treasures pulled from riverbeds and mountain seams in Burma and Ceylon. They adorned crowns, sanctified relics, and bought armies. Verneuil's achievement changes something more fundamental than commerce. It proves that a gemstone, long thought to be a gift of geological chance, can be engineered by human hands. Verneuil's apparatus is elegant in its simplicity. Fine alumina powder, laced with a whisper of chromium oxide, sifts through a vibrating hopper. It falls into a hydrogen-oxygen flame burning at over 2000 degrees Celsius. Beneath the flame, on a slowly descending ceramic pedestal, molten droplets solidify into a single crystalline column called a boule. The boule grows like an icicle in reverse, rising toward the flame as the pedestal lowers. Within hours, a finger of ruby stands where nothing existed before. Verneuil publishes his method in 1904, and the world takes notice. By 1907, factories in Switzerland and France are producing synthetic corundum by the kilogram. The jewelers of the Place Vendôme are unsettled. The watchmakers of the Jura Mountains are delighted. Synthetic ruby, harder than steel and cheaper than mined stone, becomes the perfect bearing for precision timepieces. Every pocket watch, every marine chronometer, every scientific instrument requiring a low-friction pivot begins to sparkle with laboratory-grown jewels. By the outbreak of the First World War, Verneuil's process is a strategic industry. Synthetic sapphires and rubies flow into gauges, compasses, and gun sights. Auguste Verneuil dies in 1913, just before the war he helped mechanize. He leaves behind a technique that will remain, for over half a century, the dominant method of crystal growth on Earth. The interwar years belong to industry. Firms like Jeverhergian in Switzerland grow tons of corundum in furnaces that never sleep. The crystals are sliced into watch bearings, drawing dies, and phonograph styli. But somewhere in this quiet expansion, a second story begins to stir, a scientific story that will transform the 20th century. In the 1940s and 1950s, physicists are searching for ways to amplify light itself. They know that atoms, when properly excited, can be coaxed to release photons in coordinated bursts. What they need is a medium, a crystalline lattice pure enough, stable enough, and transparent enough to hold those excited atoms in disciplined ranks. They need, in effect, a very special gemstone. The candidate is already sitting on laboratory shelves around the world. Synthetic ruby, grown by Verneuil's method, contains chromium ions suspended in a perfect aluminum oxide lattice. Those chromium ions absorb green and blue light and re-emit a characteristic deep red. To a jeweler, this is beauty. To a physicist named Theodore Maiman, this is the raw material of a revolution. It is May 16, 1960. In a laboratory at Hughes Research in Malibu, California, Maiman wraps a small ruby rod in a helical flash lamp. He pulses the lamp with a burst of electricity. The chromium atoms drink in the light, then release it in a single, coherent flash of pure red. The first laser has fired. The word laser stands for light amplification by stimulated emission of radiation. Its heart, on that day in Malibu, is a Verneuil-grown ruby less than 2 centimeters long. What Auguste Verneuil built to imitate a jewel had become the foundation of an entirely new physics. The gemstone, once ornamental, is now instrumental. Within months, laboratories across the world race to build their own ruby lasers. The applications multiply with astonishing speed. Surveyors use lasers to measure distances with millimeter precision. Surgeons use them to weld detached retinas. Engineers use them to drill holes in diamond dies too hard for any conventional tool. In 1962, a ruby laser fires a pulse at the moon and detects its faint reflection 2.5 seconds later. Verneuil's crystal, in less than 60 years, has traveled from the watchmaker's bench to the surface of another world. The bridge between jewel and instrument, between adornment and knowledge, has been fully crossed. But ruby is only the beginning. Physicists soon discover that sapphire, yttrium, aluminum, garnet, and other engineered crystals can host different dopants, neodymium, titanium, erbium. Each combination produces light at a different wavelength, tuned for a different task. Crystal growth becomes a discipline in its own right, and the Verneuil furnace, once a curiosity, becomes an ancestor. New techniques emerge to meet new demands. The Krauski method, developed by a Polish chemist in 1916, pulls single crystals from a molten bath with jeweler's patience. The floating zone method, refined in the 1950s, purifies crystals by passing a molten band along their length. Each method extends what Verneuil began, the deliberate, controlled birth of matter in perfect order. By the 1970s, synthetic sapphire is being grown in slabs the size of dinner plates. It becomes the window of high-pressure chambers, the substrate of semiconductors, the transparent armor of military vehicles. The stone that once decorated a bishop's ring now shields a soldier's optic. The lineage runs unbroken from the Paris laboratory of 1902. In the 21st century, the descendants of Verneuil's boule are everywhere. The face of nearly every smartphone camera lens is protected by synthetic sapphire. Barcode scanners, fiber optic networks, and DVD readers all rely on laser light born inside engineered crystals. Even the machines that etch computer chips depend on gemstones grown in furnaces. The Ruby laser itself has largely been replaced by more efficient successors. Yet its legacy is written into every scanner at every supermarket checkout, every measurement taken by a construction crew, every corrective procedure performed on a human eye. What began as one man's attempt to make a red stone glow has become an invisible infrastructure of modern life. It is worth pausing on the arc of the story. Auguste Verneuil set out to imitate nature and ended by transcending it. He grew gems not to deceive the eye but to serve the mind. His crystals became the raw material of watches, of instruments, of communications, of surgery, of light itself. Few inventors have reached so far while asking so little recognition. Somewhere tonight, a Verneuil furnace is burning. A slender rod of ruby or sapphire is rising toward a flame, atom by atom, as it has for over a century. And somewhere else, a laser is pulsing, a lens is focusing, a signal is racing along a fiber of glass. The gemstone, once mined from the earth, is now grown for science, and the light it carries is the light of a world remade.